All right, so this, as I've said, is the most important project in the course. So you go here to Projects, and we're down here to ED202, which is the basic Linux buffer overflow. This is the one that started it all, the same one that was written up by Aleph Null in FRAC years ago that taught us all how buffer overflows worked, and all other exploits are based on this one. So we need a vulnerable program, and here it is. It's pwd.c. Oh, yes, pardon me, I got to be in a different directory. Okay, so here's my program. All right, so what this does, main is down here. That's going to call a function called testpw, and if that returns 1, it's going to print fail, and you would win if that returned 0. And then here's testpw. It's got a password with room for 10 characters, and then it inputs up to 50 characters and puts it in passwords with the possibility of an overflow. And then no matter what the password is, it always returns 1. There is no possible right password, so you always fail. You will never win. And there is a win function, and so the goal is to trick it into running the win function. All right, so you compile this thing as 32-bit code, same way we've been doing it with GCC minus M32, and then you get this program called password32. And if you give it a password, it tells you fail. Now, the other thing is, my machine, probably notice how this number is the same every time. That's because my machine, I tested this project earlier, and I left ASLR turned on. So I'm going to turn it on now, so you can see it. This is how you control address space layout randomization. And by default, all modern operating systems have it turned on. So I'm going to turn it on again. And now, if I run that program, password32, and give it a password, and run it again and give it a password, you can see the address where it's storing the password keeps changing. D47 to CBF and so on. This is to prevent the attack we're about to do. As we're going to see, in order to do the simplest form of buffer overflow, you have to know where the program is loaded. And so we're going to turn that off. So we enter this mode, root, and then you put 0 in that system variable, randomize VA space. And then, now we're back to where I was at first there, where if I run this program and give it a 1, and run it again and give it a 1, and hit the right button, and again and give it a 1, you see it's always the same, FFFF, D5, F6. Now, programs are not randomly located in memory, and so the simplest buffer overflow will work. So we can debug this program with GDB, and I can list the program's source code because I compiled it with the connection to C source code, so we can see the C source code. And you can see line 9 is after the overflow, after we read something in and put it in a container that's too small. Here we're about to return, and I'm going to put a breakpoint here so I can examine the condition of memory before it attempts to do that return. So I put a break at 9. All right, and now I'm going to run it and give it a short password that will not overflow the buffer. I've just 10 characters, which is what it's designed for. So I give it 10 A's, and now it hits the breakpoint. So to see what's going on, I do info registers. So always what I do, info registers, and the only thing I really care about is the stack pointer and the base pointer. The stack frame for this process goes from 5B0 to 5C8. It's not very big because we got very simple small programs here. And now I can examine that with X12X, ESP. I remember that the base pointer is 5C8. So I got to get rid of that slash and put in a space. All right. And I got to make my window a little bigger. There we are. So this is the 32-bit word starting at 5C0. This one starts at 5C4, and this one starts at 5C8. So this is the stack frame from 5B0 to 5C8. That's what it means. So those are the local variables, and here is the return pointer. 56, as you see, 55, 62, 61. That's the address it will return to when it returns from this subroutine. And here is the letters I put in. 41, 41 is the first 2 A's. Here's 4 more A's and 4 more A's. Those are the 10 A's I put in. So you can see how it works. The local variable stored on the stack and the return pointer down there. And since I only put in 10 characters, I did not overflow the buffer. And so if I continue, it will finish and say fail and end normally. All right. So now if I do the same thing again, but I put in a longer password, so I run and put in a longer password. Now, when I look at the registers, ESP and EBP are still the same, 5B0 and 5C8, which is the problem. If we use the Debian machine we made, or could we use the Kali machine instead? I think it'll probably work fine on Kali as well, but I did it on Debian. Either one should be fine. Anyway, so you have 5B0 to 5C8. And by the way, one thing that's really important is, of course, one of the most common mistakes all the students make is that they use the same addresses in my example. You'll have to make the addresses appropriate for your machine, but we'll get there a little later. All right, so anyway, now if I examine the stack, this is the fundamental problem, right? The stack did not get any bigger. So 5B0 to 5C8 is here. And you see we stomped this. 46, 46, 47, 47 hit this. So that's FFGG. So now if we continue, it's going to crash, and the instruction pointer has this number, 46, 46, 47, 47. So we can control the instruction pointer. We can put anything we want in there. Whatever we put in this password as the last 2 F's and the first 2 G's, those become the 32-bit instruction pointer. So we can put anything we want in there, and the thing to put in there is the address of win. So if you disassemble win, you'll see where win is, and here's where it is. It's at that address, 56, 55, 62, 17. So we need to print that address at the end of the string, and I'm going to use Python to do that. And I wrote this code back when we were using Python 2, and Debian still has Python 2 in it, so I'm going to just keep doing it. Now I could leave the disassembler and come back, but I prefer to just use another window. Let me make this a little bigger. All right, I have another window going back to the same machine. And so this is exploit PWD 32. So I'm just going to cat it since I've already made it. 32. All right. And so here's the program. I can make it bigger, I suppose. All right. So here's my attack code. It's got A's up to the F's. Then it's going to have the extended instruction pointer. And then it's going to have the postfix. So I'm going to print the prefix, the EIP, and then the postfix. By the way, there's a general principle here, which is not really necessary in this case, but it's a very good practice. The original thing I did to observe the crash, I injected this, 4 A's, 4 B's, up to 4 J's. So I'm going to make sure I always put in exactly the same length of input. This is important. This will come up later. If you vary the length of input, you might actually hit a different crash in the program. So I found out that the extended instruction pointer is here, and there's some extra characters after it, but I'm just filling in so the total length of it stays the same. And now I just have to put the right value in for the EIP. Now to get that value, I go here, and I see win starts at 56, 55, 62, 17. And I just pasted that in here in a comment, so I wouldn't have to hunt around for it. That's the target address. The problem is strings go in order, bytes in order, and the, let me just bring this to the front so there. And so I have to put these in reverse order. So the last byte, 17, goes here, then 62, then 55, then 56. And this is how Python has you put in a raw hexadecimal value. Instead of a character like A, which would be 41, you put in this. And do we have to add the postfix? No, in this case, you do not need the postfix. It'll work fine without it. But when you do vuln server, when you do Windows exploitation later, it matters. That's all. So this is just the postfix is not really necessary here, but it doesn't do any harm. So that's what happens. This program will do it. So if you run this program, which is exploit pwd32, here it is printing out A, B, C, D, E, and then in the middle, it's got these funny characters instead of GGG. And I think one of them was unprintable. So that's what it did. It made a, sure, that's why I'm watching for these. So that's, now, just for convenience here, I take the output of that program and put it in a static file called attack pwd32. If I do ls-l, because I'd like to have it right here, 41 character attack file, because then I can easily feed that into my code in the debugger. So when I ran this program before, it asked for input from the user. But if I run it this way, it's going to take less than it's going to take input from that text file instead of from me. Now it's still got the breakpoint in it, so it's going to run. I'm going to say start again. It's going to go to the breakpoint, but now it didn't ask me to type in the password. It took it from that file. So I can do info registers, and I will find that, of course, these have not changed because that's the problem. The stack does not get bigger. It's the same size, 5B0 to 5C8. So if I look at the stack, that's this one. 5B0 to 5C8 is here. So now here's the 45, 45, 46, 46, but instead of just stomping this with 46 and 47, I've carefully put in this address, 56, 55, 62, 17, and that is my win address. I can even check it with disassemble, win, and you can see 56, 55, 62, 17. It looks right, so that means if I continue, it's going to print you win. So it entered the win routine, and then it crashed because we did some collateral damage by not restoring EBP as well. So our exploit was a little bit sloppy. It achieved the goal and then crashed, but you know, this is we have gained control of the machine. We managed to make the machine do something that the developer did not expect. So we did gain control. Now, we didn't actually inject shellcode of the type we were talking about today and make it phone home to a command and control server. We'll do that later. But what we did here was we tricked it to do something that it was not supposed to do by controlling the instruction pointer. So that's the essence. And now everything in the whole rest of the course is just going to be enhancements and variation on this theme. So the next thing you might want to do is, you can check it outside the debugger, by the way. This is running inside the debugger, and one problem, which will come up a lot in this course, debuggers are not very accurate. The actual addresses and stuff are a little bit wrong in the debugger, so sometimes when you get an attack working in the debugger, it won't actually work outside the debugger. So you always have to check it, and you sometimes have to move things around by a few bytes, like up to maybe 50 or 80 bytes, to make it work. But in this case, you see it does work outside the debugger. I can run password32, feed in the data from attack password32, and again I get the UN message. And then it crashes. So my exploit is doing what I expected it to do. So the first variation is, what if you had 64-bit code? You can just compile it without the M32 switch, and it'll be 64-bit code. And so now you can crash that. So if you have /pwd64, okay, it asks you for password, and there it says fail, but if you give it a long thing, then it crashes. So it still has the same vulnerability. Notice the addresses are much longer. These are 64-bit addresses, 8 bytes instead of 4 bytes, but the address still does not change as we run it over and over, because that system-wide variable turning off randomized VA space affects the 64-bit code as well as the 32-bit code. So we can debug it the same way, and we can see the source code. It's going to be just the same source code, of course, because we took the same source code and just compiled it to 64-bit machine code. So line 9 is the line where it tries to return to the calling routine, and this is where we take over the machine after the overflow. So we still want to break at 9. And then we can run it and feed in a 10-character password to see the operation of it normally. So there's my 10 A's. And now if I do info registers, notice there is no EIP, no ESP, and no EBP. Those are the 32-bit registers. 64-bit registers use an R. So here's the relative stack pointer and the relative base pointer, the register, stack pointer, register, base pointer. And someplace is the RIP, the instruction pointer, which, yeah, here's the RIP. So the stack goes from 480 to 490. So I can do the same kind of examine, 12x, but I got to go from RSP instead of ESP. And so when I see my SP and BP go from 480 to 490, this is the 64-bit value starting at 480, and this one starts at 488, and this one starts at 490, and this one starts at 498. There's only two 64-bit values per line now, and this tells me to go from 480 to 490, so that means this is the stack frame with enough room for three 64-bit values. And this is the return pointer, 5555 51C6. This is the address where it's going to resume operation at. Here's the A's I put in there, 4141, just like before, 10 A's in a row. And once again, the 10 A's fit in the stack frame and don't overflow it. But if I put in a larger injection, it's going to overflow it into the 64 bits there. So here's my longer injection. So I can run and say yes, and put in that longer password, and I can examine the registers, and once again it goes from 480 to 490. It did not change. And so if I examine the stack and highlight the stack frame from 480 to 490, again I see here I am stomping it, 4545, all the 46s and some of the 47s. Now it takes 8 characters to fill it, but again it's the E's, all the F's, and some of the G's. Those are the characters that hit. So I can make my Python file, and it's going to be very similar. So I should be able to go here, and if I look at my Python file, that's exploit 64. All right, now I'm going to need the address to attack. So let's disassemble win. All right, and here's the address. It's 51A5 at the end. A bunch of 55s and then 51A5. So here's that address, 51A5. Here's the prefix. Here's the EIP, which is now 8 bits long, and I probably should have called it RIP to be like perfect, but I didn't think of that when I wrote this Python. And there's the postfix. So again, you have to take this value and just put it in there backwards. A5, 51, then a lot of 55s, and then some zeros. And notice, by the way, that I fill it out to here, but from what I told you before, you should realize it's never going to see anything after that 0. That 0 is actually going to terminate the string, and the rest of this is never really going to go into memory. It turns out to be okay, but you know, just like before, this postfix is sort of there as a matter of style and not really effective, but it doesn't do any harm. And if you run this program, 64, again, it prints out all the letters out to J, but in the middle, there are some funny letters. Some of them non-printable, which are this mess printing out. So I can run, I take that and I put it in take the output of that and put it in a file called attack pwd64, and now I can run it in the debugger, taking the arguments from here. So if I do this, that's going to run it taking my attack code, start it from the beginning. Okay, and now if I do info registers at the breakpoint, RSP and RBP are still 470 and 480, 10 points apart. So if I examine the stack, 470 to 480 is here. And this is now not nonsense anymore. Now it's a bunch of 55s and then 51A5, which is the address for win. So when I continue, it's going to print you win and then crash. So it works inside the debugger and it'll work outside the debugger. All right, so that's the simple case of a 32-bit and a 64-bit buffer overflow. And now you've got some other challenges here, and these are fun. This one here, I remember I wrote this on the airplane on the way to DEF CON China. I realized that I could write a server that's running this code, and I could automatically put a debugging script on the server that you could get from PHP. So this is going to run something on the server. You don't have to install anything. So if I put in a string like AAAA and then debug, it's going to go up to my server. Here it's going to print the source code, although I've redacted some flags. And then it's going to show you, it puts a breakpoint at line 8. So this program here has a main. It asks you to enter a product key, which you can put in up to 100 characters. Then it calls something called activate. Activate copies that into something that only has room for 25. So you can put in up to 100 characters, and here there can be an overflow. And then if the 30th character is 7, you get a flag. And then it always returns 1, which causes you to not win. So you get the first flag by just figuring out how to put a 7 in the 30th location. And you get the second flag by figuring out how to execute this win function. And here it's going to run with the input string that came from the user. And all right, and here it's going to disassemble win. So there's the address of the win function. And then it runs the registers, and then it prints out the stack. So you can see what's going on here. So what I did here was I fed it AAAA, 4 A's. So if you look at the registers, ESP and EBP are here from 20 to 48. Here's 20, here's 40, 44, 48. So that is the stack frame. There's the return pointer, 56, 55, 57, 64. I get some of this. And here are the A's I put in, 41, 41, 41, and there's the other. Those are the 4 A's I put in. So there's no buffer overflow. You can see I'm going to need to put in a lot more to overflow it. All right, but my first goal is now the easiest way to do this project is to just build this URL in a text editor. So I'm going to put that here. All right, we make a new one. Rip it off and put it here. All right, there is the URL. And the easiest thing to do is to just modify that URL. So let me go back and let's get my challenge. My challenge was, okay, first one is to send a character string 31 characters long ending in ASCII code 7. So this is 4 characters. Let's make it 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. D. There's 31 characters. 10 A's, 10 B's, 10 C's, and 1 D. Let's see what that looks like. I just copy that and put it in a tab here. All right. It's going to, my ESP is here and my EBP is there from 20 to 48. So the stack frame goes here. And here I have A's, and then I have 42 is B, 43 is C, and then I have a 44. So that's what it does. Now, I wanted the last character to be a 07. And to put a 07 in a URL, you just change this to %07. That's how you put in a binary hexadecimal value in a URL. So that should reveal a flag. I'm going to put in a 6, just so I don't reveal the flag on the video, but that will show you the point. So if I put that in there, then I should be able to see ESP and EBP. 48 is the end of it, there. I have 43, 43, 43, 43, and then I have a 06. So if I put a 07 there, now when it continues, it's going to just crash with a segmentation fault. But if I didn't, anyway, if I had a 07 there, it would continue and print out a flag before crashing. All right, so that's one thing. Now to hit this win function, all I need to do is figure out how to hit the instruction pointer. And that's, if I go down here, 48 is where the instruction pointer is. This is 48. So I need to go a little further than where I have. I ended up here. So I should be able to hit it by just adding more characters here. So let's go here and put like, I'm going to put 1, 1, 1, 1, 2, 2, 2, 2. There. That should do it. And let me put that in my text editor so it's easier to see. I'm just going to try this. Someplace over here is junk that's going to hit the EIP. So if I run that, and I go down here to ESP to EBP, 20 to 48, there's 48, and 1 in ASCII is 31, and 2 is 32. So it looks like the EIP is hit by the last 2 2s and the first 2 3s. So right here, those 4 characters control the EIP. So if I make another copy of this thing, and I put in those characters, I'm going to put in A, B, C, D. Actually, let's use percent. So percent 01, percent 02, percent 03, percent 04. There, just to make sure I'm hitting it. If I got it right, those 4 bytes are going to go in the instruction pointer. Let's take a look at that. All right, and so it's the EBP is C48, which is here, and there it is, 01, 02, 03, 04. So it looks pretty good, and when it continues, it's going to crash with 01, 02, 03, 04. So now I control the instruction pointer. So all I have to do is find where the win function is and put that address in here, flipping the bytes backwards, and up here you've got the address of the win function. So it should be a minor variation on this to get you there. And that's the point. So this one here, you can find flags by controlling the input. And here you just do the same thing for a 64-bit processor. And here you can do it for one that has address space layout randomization turned on. If I put in characters here and debug it, it's in GDB, and GDB turns off the randomization, so it's always the same, and you can examine the stack and such. But the next one, when you run it, it's going to first show you the address of win function, and now you have to figure out the right string to put here, including that. And this is different every time. This time the win function is 7480F, and if I go back and do it again, it's different. So there's 2 flags. There's one you find in the debugger where there's no randomization, and to get the next flag, you're going to have to use this address to adjust your exploit to get in. So that's what I wanted to show you, and I'm quite happy with this. This is, I think, a very good way to thoroughly understand the buffer overflow. And if you understand that, that's the meat of the course, and all we're going to do is minor variations on that as we go ahead. So I'm going to stop the recording.